right. Excuse me. Welcome. How is it possible that the semester is nearly over? It flew by. Yeah, let's clap for that. The problem is for you. Yeah, okay. The problem is for you, it doesn't feel at all over because you have all this stuff you have to do before it finishes. But and I play some role in that. My apologies. So we're going to, unfortunately, talk about a little bit more content today. I felt it was hard to not feel derelict in my duty if we didn't talk about flash-based SSDs a little bit and how they work. So we're going to do that today. I'll do that for most of class. And then at the end of class, we'll do a little wrap-up, just some last thoughts, a little bit more generally beyond just class. I'd like to just share some thoughts with you at the end. And then we will be done with lecture. And then we just have left a project and a final. So that's what's in front of us. How quickly it went by. Hard to believe. And can everybody hear me in the back okay? My last time I'll ask that. Okay, thank you. All right. So today, the last day. I'm going to move this chair. We're going to cover what are called flash-based SSDs, solid-state storage devices. Sorry, did someone have a question or just excited to talk about flash-based SSDs? Okay. So, when people talk about solid-state storage, well, actually, what do they mean? What does that term mean, solid-state whatever? You're like, that's what you're supposed to tell me. That's why I came to class. Okay, what's the answer? Yeah, no moving parts. It's like circuitry, right? Like the rest of the computer. Like it's actually very strange if you think of it. We think of computers as these advanced electronic things, but for years they had the hard drive, which is very mechanical, right? Like it's got all this mechanics and chemistry and all this crazy stuff in it. Solid state storage, solid state, right? What that means is, it's just circuitry, right? And electronics. It's no longer is there an arm, that moves across the surface or rotating anything, right? It's just all in electronics. And of course, that naturally is going to promise that it's likely to be faster and perhaps much faster than a hard drive. Hard drives are going to be limited, like we can only build motors that are so fast, right? That's just we have physical limits to that. And of course, we can only build circuitry that's so fast, but as we know, like with processors, we can build things that run this crazy rate, right? Billions of instructions per second. So presumably, we're going to get some performance advantage. So we're going to talk about flash-based SSDs. Just like hard drives, they're persistent storage devices, right? And when it's just another persistent storage device, meaning that if we unplug it, the data stays in it, right? It's non-volatile, as opposed to like DRAM, which is volatile. And we'll talk about a bunch of the basic things. We'll talk about some basic characteristics. Where we'll talk about kind of how it works. Now, we're not going to go into the double E's. If there's some double E's in the room, my apologies. We're not going to go to that level of understanding. We're going to rather get a systems level understanding of SSDs so that we can then understand how we might use them in a computer system. And once we do that, once we have the basic characteristics, what we have to go from the raw, what you might call raw flash, to something that looks like a storage device. We already know what storage devices look like. They look like a bunch of blocks you can read or write. We're going to see that actually kind of how flash looks by its nature is a little different than that. And so what we're going to have to do in building a storage device from raw flash is figure out how to map the API that we want, reads and writes of blocks, down onto what the flash provides, which is a little bit different. And we'll see that in a second. And by doing that, we're going to see actually just previewing some key, of course, we're going to talk about the techniques that we need to do this. And just previewing that, I guess I could make that parenthetic. It's really just part of this thing. What we'll see is that our old friend log structuring, which you're getting to know better and better and maybe dislike a little bit. There's a certain love-hate one has with projects that one's doing, right? That one is doing. But we'll see how log structuring actually comes into play inside of a flash-based SSD as well, all under the hood. So you don't actually see it as a client of the SSD. So that's what we'll do for most of class. And like I said, for those who came in late, we'll do that. We'll kind of go straight through, and then I'll just do some kind of final words for the last 10, 15 minutes, some reflections. We'll be a little more philosophical and end on a different kind of note, I think, than typical class. Okay. So let's start talking some of the basics of our flash-based, or flash, right? So when we're talking about flash, we're talking about a specific type of flash. There's different kinds. It's called NAND flash. And at its very core, what we're doing at a low kind of electronic level is we're figuring out a way to trap charge in silicon in some sort of little gate. It's called a floating gate. And by trapping charge inside of it, that means like even when you unplug it, you're actually trapping some charge in this little tiny thing. And that means you can therefore encode, a bit into it, bit or bits into each little well of storage. And that's literally the level I'm going to talk about it in here. There's so much more detail. You have to understand that really deeply. But we're not going to do that in this class because we don't really have the background. You can, of course, inside of one of these little gates, you can store just a single bit, so like a high charge or a low charge, or you can store multiple bits, high charge, medium high, medium low, low, and map those accordingly. And there's some names for that, but we'll kind of ignore that. So we're just having a way of, we have some electronics, and we figure out how to store some bits. Fascinating and not very deep. What we then turn that into is like a collection of those gates or into something we'll call a bank, or maybe sometimes we can think of it as a chip level interface on top of many of those bits. So this is a collection of many, many bits. And what we have to think of how this is going to work, and this is a little bit strange, is we don't have the same read-write interface that we expect. And there's, again, low-level reasons for this that relate to electronics and low-level reasons that relate to cost. But we're just going to take this as kind of a face value. So on one of these chips, we have the ability to do what we call a read. So that's just like you expect. And that's done what in the flash terminology is over what's called a page. A page is something like, typically 2 kilobytes or 4 kilobytes in size, something like that. And that's a little bit confusing because when we think of a page in the OS context, we think specifically, that's a 4K thing, for example, and it's hardware defined, and like in x86, it's defined by the hardware. But there's a slightly different, sometimes similar, sometimes different page unit granularity thing inside of a flash chip. So I'm going to draw a picture of a flash thing over here. And let's say we have this is like a page of it or something like that. And we can direct a read to that page by just passing an address and reading that page. So that part feels kind of similar and not that interesting. It turns out writing it, though, is a two-step process. And this is where some of the interesting, what you might call architectural decisions are going to come into dealing with flash. The two-step process is before you can write to any flash, you have to put it in a mode which is called erased. So you have to run an operation which is called erase. And erase essentially prepares a chunk of the flash to be written to. And in fact, that is not done at the page granularity, but rather the block granularity in flash terminology. Block is something different, and a block is bigger, that contains many pages. So a block might be, for example, 256 kilobytes in size or something like that. So a block inside of a flash, let's call it a chip for lack of better terminology, has many blocks in it, and within each block there are many pages, okay? So in this example here, let's say, just for simplicity, this is a page, and let's call this whole size thing a block. Okay, so the flash consists of many of these and, et cetera, right? So that's a little weird. And again, one more operation. The other operation, which is what we would think of as writing, is called in flash terminology to program. And the programming happens at the page granularity. So how that works, so read is already similar, but basically to write anything, I guess I'll just reiterate this, you must erase the entire block, and at that point, you can program each page within the block exactly once. Okay, so let's say we wanted to write information into this first so many pages of this first block of the flash. We would first erase the entire block. You can think of that as changing the state of each block to erased. And then we have the ability to program each one of these, and we would likely do it in this order for reasons that we don't have to talk about. So then we might program this one and fill it with data, and it would go from erased to becoming then something that we might call valid. So and valid means it's been programmed, right? And you can read from it. And then you could program the next one, right? You could say, okay, I'm going to put some data in here, and so forth, and on you go. Now, per our nature, this is just, again, the nature of the technology, and like really understanding that is a much longer series of lectures, so we're just going to accept this. So, long story short, now I might program all of these and put valid data inside of them. That sounds good. If I want to change anything inside of here, let's say I want to change what's in here, I don't really have the ability to do that very directly. What I have to do if I want to change any bit inside of here at all, inside of this first block that we just programmed, what I'd have to do is erase the entire block again, and then I can program it again. Okay, so again, that's the nature of any writing. You have to erase the entire block to move the block to a state where it is programmable. Then you can program each block, each page within the block exactly once. And if you want to rewrite, or to, let's say, overwrite it, then you must erase and program again. So that's pretty weird, but it's the nature of the technology. It's not like the technology, we wouldn't say like this is how we wanted it to be, it's just what the technology is. And why that is, again, I would say it's beyond the scope of the class. So does that make sense? There's three operations, not two, not just read, write. There's read, and then there's this pair, erase and program. Read and program, or you can think of it as read and kind of actually doing the write. They're at the page granularity, which is again smaller, like 4K, let's say. But erase, because again, the nature of the technology is over the big block. It's over the whole block. So that erases the entire block. And of course, if you erase the block, you lose everything inside of it. So if you care about what's inside of that, you better have done something about it before then. Any questions about that? Okay. So let's do a few characteristics of like performance and reliability characteristics. I guess I'll erase this. We'll have to understand those performance and reliability characteristics in order to build a full-fledged device. Okay, so let's talk about performance first. And you can think of performance in terms of the operations, read, erase, and program. And we should just, these are ballpark numbers. Of course, they change across generations and so forth. But you can think of reads as being in the tens of microseconds. How does that compare to a hard drive? What would you say a hard drive is? Someone says, hey, you're taking that OS class and you learned a lot about hard drives. What order of magnitude timing are we thinking about with a hard drive? Yeah. Milliseconds, right? Milliseconds versus microseconds. That, as you should know, right? A millisecond, a thousandth of a second, a microsecond, a millionth of a second. So we're off by 3 orders of magnitude almost. So it's much faster than a hard drive, right, to read. Much faster. Much faster than a hard drive. And if it were much cheaper, we wouldn't be talking about hard drives at all. It's not. They're still more expensive, and they probably will be for many years. So that's why we still use hard drives. That's a read. A program, so writing a particular page, that's more on the order of hundreds of microseconds. I'll put mu for microseconds. Same thing, mu, micro. So a bit slower, but still way faster than a hard drive, right? Hard drive being milliseconds is kind of the way to think of it. But the really costly operation is erase. Erase you can think of as being a few milliseconds. And that's much more like a hard drive. So if we're doing erases all the time, it's going to be problematic. It's going to make the SSD quite slow. So when we're thinking about design of the structure of a storage device that is built on top of flash-based SSD, we're going to be thinking about, certainly from a performance standpoint, how to not do erasing very often, if we can help it. Okay. Let's talk about the reliability characteristics. Of course, it's different when you have a solid state device. When we had a hard drive, it was mechanical, like the motor might break. The head might crash, all this crazy stuff might happen. But generally when we read and write it, like if the drive is working and the mechanics are working, we can read and write it. No problem. Flash is a bit different. In particular, it has the major issue it has is something people call wear out. And wear out is pretty easy to understand, at least conceptually. What it is the case where I guess maybe write it this way. Once you erase and program the device, let me say a block, too many times, we'll say too many, it stops working. And what is too many? Well, you might be somewhere between like 10,000, maybe 100,000, something like that, times, something like that. Depends on the technology. The more bits you pack into each of those bits, like into each of those gates, actually makes it so it's fewer. So if you try to make a denser device, it's more likely to wear out more quickly. Something fell off of my face. What was this? So, by the way, like with the mask on, I like run out of breath more quickly, and I feel like I'm recording myself like heavy breathing, and it's really disturbing to me. So I'm listening to myself breathe up here, and then have you ever thought about breathing, and then you like think like you become bad at breathing? That's what's happening to me all the time up here. But anyway, so if it sounds really, if you're listening to a recording like now, if you're not here and you're listening to the recording, or if you're later to listen to it and you hear me breathing, I'm trying not to do it weirdly, but it's unfortunately coming across very strange. And this is one of those things, like 1 second into it, I'm like, why am I sharing this? So, complete mistake. But anyway, amateur mistake. Talk about something weird. Okay, so anyway, wear out is our primary problem in this flash-based world. And that's kind of interesting. What does that imply? If a particular, this is again at a block level. Like, we're worried about if a particular block, if we erase it and program it over and over again, it's going to become unusable. What's the implication for a system design standpoint? Yeah. Yeah, you need to spread out writes, right? You can't, like, for example, when we designed a particular file system like the fast file system, like one of the simple or the very simple file system we looked at first. It had inodes in a particular part of the disk and data blocks in a particular part. If then you were updating a particular file's inode over and over again, like you could just wear out that part of the disk because it's a fixed mapping, right? So we're gonna have to think about how to spread writes out so that the drive, the SSD in this case, degrades evenly, okay, across over time. Otherwise, you'll just wear out parts of it. There is some other failure modes that we can think about, but we're not going to talk about too much today. In particular, if you program a particular page within a block, you have some chance of kind of changing the bits in neighboring pages. So, and that's called program disturbance. So we tend to just program in order to kind of minimize that, but we won't really talk about that. So just something to know. Okay. So we have performance characteristics, and we have reliability characteristics. And now we have to think about how to take those and build a device. And the device that we want to build, like an SSD, a solid-state storage device, is what we would call, just like our hard drive, we would call it a block-level device. So that means our API should be basically to read or write a particular block. So immediately, as I guess previewed earlier, you can see our challenge. We need to take our reads and writes of blocks, which is like for example, your file system is built on top of an interface like that, and turn it into, well, reads probably map to reads, but writes at the API level here have to map to erases and programs in some form. So somehow we have to map this down to read, erase, and program. Okay, so you can think of the device then as being something like this. Inside of it, somewhere it has a bunch of flash chips. So these are the flash chips. In many ways, you can think of those as being kind of like it's a parallel storage device. So unlike a single hard drive, even though it's so complicated, you can just do one I/O at a time, right? The only way we get parallelism in a hard drive-based storage system is by having a RAID, like by having many hard drives. Inside of a single SSD, like it's in your laptop or in any machine you buy these days, essentially, it's a parallel storage device. So there's many of these flash chips inside of there. How could you tell, actually, just empirically, that a storage device is parallel versus sequential? What could you do to kind of give yourself some evidence of it being a parallel device? One, you could look it up, but what about empirically? What could you do? What kind of test could you run? Yeah. Could ask for the same things over and over again and see if the order changes. I was thinking about doing something more with timing. Like, what could you do with timing? I don't know if your technique would work. It might, but I was thinking it might be something simpler. What's the property of a parallel performance, a device that has parallelism inside of it? Yeah. Yeah, you might, for example, send some number of requests to the device, and if they kind of come back to you in the same time that a single request does, you might be able to tell that those must have been serviced in parallel, right? If they happen to get directed to different flash chips, just like in a RAID storage array, if you send a bunch of requests to it, they could be serviced in parallel, right? So it would go fast. It would be many requests could be finished in the time of one request. If you can generate a scenario like that, you have probably a good idea that it's a parallel device. So you can certainly try that, and it will be true on your local flash. All your flash devices that you buy, the flash-based SSDs you buy today, have parallelism inside of them. We're not going to really focus on that. It's just something to know. But again, what's coming in the top here are reads and writes. And so somewhere inside of here, there has to be some kind of controller. And when people say controller, by the way, all they mean is something like a little microprocessor, something that's going to take those requests and then figure out what to do with them, and then return the data or whatever as need be. The controller, of course, has some memory too. It might have some DRAM or something like that, or SRAM, some kind of RAM. And I won't draw like bus structures and things like that, but basically what we're going to do is we're going to take requests, we're going to figure out how to map them onto these flash chips, and somehow we're going to turn reads into reads, and then somehow we're going to turn writes into erase and program. So what we'll do here is first we'll do it in kind of a naive way. First we'll figure out how to do this in a naive way, and then we'll do a better way which actually kind of works. This has too much chalk on it. Okay, so it's actually quite amazing in a modern storage device, whether you're talking about an SSD, which are actually pretty simple, or a hard drive, which are fairly complex. They all have processors inside of them, and those processors run a lot of code. Like a modern hard drive, maybe we talked about this, has hundreds of thousands of lines of code that are running inside of it, low-level code that are operating the hard drive. And same true for any flash-based SSD. So let's do kind of a naive approach, which you might call, let's say, a direct mapped approach. So a direct mapped approach would just basically say, well, here's our interface. And it's a bunch of blocks that we can read or write. So we can do a read or write to this. Sorry, I'm running out of chalk here. Let's see if this one works. And we have to map that onto these, like a flash chip. And so let's say we kind of do that directly, meaning, well, in the flash down here, remember the flash has these blocks. Let's say it has 5 blocks in this example. This is a block. And then, within each we have so many of these pages. Let's pretend it's 3. This is a page P. And then if we want to read a particular part of the interface, right, the interface that's coming down to the device, if someone issues a read to, say, this first chunk here, which is going to be a page, we would just directly read it, right? So it's direct mapped. We just read it directly. We'd keep everything statically. It's like a static mapping. Of course, that read works fine and isn't the problem. The problem that we have is, like, what if somebody wants to, for example, do a write to this thing right here? In the direct map approach, what you'd have to do is you have to do a few steps to do an update. Well, what do we know that we have to do when we're trying to update some data inside of this block? What do we have to do? We know we have to do an erase, but there might be live data in there. So what would we have to do first? First, we'd kind of have to like read it, right? So to update a block, what you think of is we'd read in the block, page at a time, let's say, then erase it, then program it in again, right, with the new data. So we would erase this entire thing, read all the stuff from it, then erase it, and then program it in, including the old data and the new data. So that's not really shown very well in that diagram, but hopefully that makes sense. So that has two problems, that approach, where to write a single page, we have to read the whole block in, update it, the part that we're updating, and then program the whole thing out. Has two problems. What are the problems? Yeah. What's one of the problems? Yeah, it's like really wasteful, right? Like you're doing a ton of I/O to just update one page. In fact, when you're doing I/O and you're doing more I/O than you need to accomplish the I/O, there's a term for that. And the term is something you would call I/O amplification. Right, we're doing more I/O than we really need to. We just wanted to write this one page out. Instead, we read, let's say, 3 pages, erased everything, and then wrote 3 pages. So it's you can think of it as a factor of 6 plus an erase, more I/O than we needed to do. In fact, I/O amplification happens all the time, right? Like it even happens in a typical normal file system because maybe you wanted to update just 1 byte of a file. When you want to update a byte of a file, you have to read in the whole block, update that byte, and then write it out. So I/O amplification happens all the time, but we can use it as a measure of efficiency. So this is bad for performance, right? What's the other worry that we have in this protocol, this direct map protocol, where you read in the entire block and then you erase and then you write it out? What could happen? The system could crash, right? You could read it all in, then you erase it, then you crash. So it's bad for performance, but because of this, if you crash right here, right, the crash could lose your data. So it's even worse. And in fact, what you'd have to do to feel good about it is you would have to read it in, write it out somewhere else, and then then kind of update this in place later, and then be able to recover. So you'd have to do a bunch of extra work. So this approach doesn't make any sense, and that's why nobody does this. And when you read papers about even the earliest of flash systems, nobody said, let's try this approach and see how it works. It's just immediately obvious it's not going to work. I mean, it does have some positive properties. It's super simple, right? Like you don't have to keep track of where anything is or anything fancy like that. Does that make sense? So our characteristics, we have these big blocks, and the problem, of course, and I mean, we didn't even talk about the other problem. It's going to wear things out, right? I mean, that's another reliability problem. If someone just writes over the same block over and over again, it'll wear it out. So let's talk about a better approach. I already hinted at this, or just said it directly, I guess. And the better approach is to use log structuring in order to kind of achieve a bunch of goals at once, performance and reliability goals. So it's a little different. It's similar to, this is why it's easier to talk about an SSD after you've talked about like a log structured file system. You already have like some idea of how these things work without getting into the details. And so the log structure approach is going to be pretty simple. We're going to essentially treat the flash blocks like a log. And what that means is all we're simply going to do is, let's say we have our blocks like this. I mean, you can probably figure this out at this point. Let's say we have some blocks like this. This is a block 0, block 1, etc. When we're writing stuff out, we're simply going to, well, erase the entire block, then program it beginning to end, right? Program, 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 etc. And then when we're done with that block, we're going to do the same for the next block and so forth, kind of filling up the disk that way. Now, that's going to introduce a problem, of course. The problem is well, how to find anything. And to do that, what we're going to introduce is just a level of mapping that is, you're kind of going to guess how this is going to go. It's something that people call the flash translation layer. Or you might hear this term a lot if people are talking about flash-based SSDs, they talk about FTLs. So FTL is something that's essentially implemented in the controller and, say, memory. So this implements the FTL. And it's just really a map, right? It's just a map for a particular, each page of each block in the API to its location on the flash. Okay, so when we're writing out, if we erase the block, then we're writing out pages. All good. But what we're doing the whole time is, in memory, this is again in memory, just track all these things. So we know where everything is. You simply, when a read comes down to the SSD, you're going to look in the FTL, which is fast. It's in memory. It's going to say, oh, that's, logical block 10 is actually stored, right here inside on the SSD itself, and we can direct the read to it directly and get our device serviced, right? Get the request serviced. So it's a very basic idea. For every block in the interface, you can think of that as for every 4K, let's say, we're going to record a location potentially of where it is on the flash at a given moment. So that's a basic idea. Just erase stuff once, and then you can see you're minimizing your erase cost then, right? It means, like, if there are, 4K page inside of let's call it or you could say let's say it's a 1K page instead of a 1 megabyte block, you can see you're doing an erase then for every 1,000 times you program. So you really reduce the number of erases you're doing to quite a minimal cost overall, because you have so many pages that you program before you do another erase. Okay, so that's a very basic idea. Let's talk about a few of the problems that we generate. Just like anything, you solve some problems and you introduce new ones. That's the world of systems in a nutshell. So some problems that we're going to run into. Well, you kind of already know about some of them. What are some of the problems we're going to run into? Maybe none. Shorter class, yeah. Oh, yeah. Yeah, great point. So if we're storing this in memory, we have an issue of, like, what happens if we crash, right? So we have to think about FTL recovery in case of crash. Great point. So there's a lot of different ways to do that. Different systems do different things. 1 second on the question. One natural way is when you're writing, there's a little bit of what people call out-of-band space next to each page that you're writing, or at the beginning of the block or somewhere like that. So you might actually record some information about the page that's being written while, on the surface itself, as well as refer to it via the FTL. And then if you crash and recover, the first thing you might do, and some SSDs do this, is they just scan their entire contents to reconstruct the FTL. So you always write a little extra information down. There's different ways to do that. But yes, this is something you have to worry about. So when writing, you just have to make sure to record a little bit more information somewhere. The mapping info somewhere, so it can be reconstructed. In fact, that made some, especially original SSDs, which didn't do this particularly efficiently, when you turn them on, it took them a long time to become ready because they just had to scan the entire surface. Kind of like an FSCK, but this is done at the device level. Yeah, there was another, it was a question or a problem? Yeah. Yeah, so let's first talk about the problem, which is that you need to do garbage collection. So, yes, you need to do garbage collection. So when you're, as the question anticipates, when you're programming something, when you're writing a particular block over and over again, I'm writing block 10 of the interface over and over again, new versions of the block are gonna show up later and later in this log. And that means we have to have a way of reclaiming the space. So we have to do garbage collection, right? Which means we have to read through blocks and figure out which parts are live, maybe copy them to a new block, and then free this block that we've just done, and then we would just erase that block and make it available for writing. I'm not sure if that quite answers your question, but you can imagine it. There's actually some different ways to do garbage collection, but that's the basic idea. So that's kind of interesting too, because it's a background activity. Like a hard drive, when you're doing reads and writes, that's all you're doing. You know exactly all the I/O activity that's happening because you're initiating it, like the OS or whatever. In an SSD, in the background, it periodically, the controller runs garbage collection. What's going to be the impact on performance of this kind of garbage collection? Like, how are you going to view the device if you're using it to build a storage system? What kind of issues are you going to be worried about? Maybe none. That's one thing. We could be worried about nothing. That's okay. But what would we be thinking? Like, how would we think about it if we're building a system out of devices that periodically do garbage collection? What might happen? What kind of things are we worried about? Yeah. Yeah, like you get kind of unexpected slowness, right? So let's say you have a bunch of SSDs and you're doing things like writing to all of them. At different times, each of them might have kind of be slower than you expect because there's garbage collection going on. It's a little bit weird. We have no control over it. Like, as a writer of the OS, right? You usually you feel like you control all the devices in the system, but there's this background activity that happens within the SSD that you do not control. And that certainly happens inside of RAID too. Like, RAID does all sorts of crazy stuff to recover from failures and so forth. But it's something we should be maybe concerned about. What else? One more kind of big issue with this FTL. It's something that you can kind of think about in every part of the class. We worry about this. We worried about it with page tables. We worry about it with structures to point to all the blocks of a file. What's the overhead we're worried about with an FTL? Well, space overhead, right? It takes up a lot of space. Space overhead of the FTL. And you can think of it. Let's say you had, you could have certainly, like how big is your SSD on your laptop? Who has like a laptop? I don't know what I'm asking. Who has a laptop? Yeah, you have one. All right. How much space is on your how much space do you have in your SSD? 512 gigabytes. Cool. So if we have a 512 gigabyte laptop, and then let's say for every 4K, let's say at a 4K underlying page size. So if it has for every 4K, you might have to have a mapping. How much space does that take up? Actually, why don't you compute that? Okay, let's do that. You do it for just two minutes. So 512 gigabytes, 4 kilobyte page size. How big is the FTL? And you could assume it's 4 bytes per entry or something like that. Sorry? Oh, what? Sorry, what did you say? Oh, you're already giving an answer? Okay, well, just wait a second. Don't get too excited. I'm going to take a drink. I should do it on here. So roughly how many entries do we need in this FTL? Yeah. Yeah, like 128 like kind of million entries, right? And then each entry might be, let's say, 4 bytes. So maybe that gets us to half a gigabyte or something like that. So you get to some pretty big sizes pretty quickly. It's a huge amount of space just to have mappings, right? So that's a primary problem of FTLs. You have to think about crash recovery, but that's not too bad. You can just kind of write down a little extra information when you're doing the writes. You need to constantly think about garbage collection, so freeing stuff up. You need to think about space overhead. How can we reduce that? We'll talk just briefly about that. And now that I think of it, there's one more thing that we didn't talk about which relates to garbage collection, which is you have to think about what people call wear leveling. Sorry, I forgot for some reason, spacing out. And wear leveling means we have to kind of make sure that we write evenly across the entire device, otherwise some parts of it will wear out sooner than others. So that's a fourth thing we have to think about in the FTL itself. So, in fact, if you think about when does wear leveling happen, it's like when you've written something just once and you just always read it, you never update it again. If you don't do anything, what'll happen is it'll just sit there and stay in the same spot. So much like for garbage collection, what you do is you go through and you read blocks and then figure out what's live and write them out. Similarly for wear leveling, you have to go through the device periodically and say, oh, this hasn't been written to in a while. I'm going to take what's in there and live and move it somewhere else and then make this so we can write to it again. So in fact, both of these, garbage collection and wear leveling, they're kind of similar, and they're both background activity that's going on inside the device. So that's kind of, yeah. Yes. No, they're not perfect. But I guess what you're getting at is like how close do they have to be to perfect for it to be kind of functional? Is that kind of what you're getting at? Yeah. I mean, basically, what they're trying to do is because if you think about depending on the technology, you're talking about a particular block wearing out after either, like, say, 10,000 or 100,000 erase program cycles. So you're trying to make sure that one doesn't wear out way ahead of the others. So that's kind of the margin you have, right? So you want to be, let's say it's 10,000, you want to be kind of within a factor of, let's say, 100 for each of the blocks of the system. So it is some activity. You're going to have to move stuff around, not infrequently, to make sure that that happens. I mean, it depends a bit on the workload. Like, it's easier if like the workload is writing to everything all the time, then you're naturally going to do garbage collection, and the garbage collection is going to move stuff around really naturally. But if the workload has a lot of reads, which most do, and some writes, then some stuff is going to get updated a lot, and it's going to naturally move around, and then other stuff is just going to sit there frozen. And so you're going to have to move that stuff anyway, and that's where you kind of pay the cost. Yeah? Yeah, I think there's not a great answer to that. It depends a lot on, like, there's been some studies out of like Google and Facebook and other places that have these huge data centers with SSDs. Certainly they last for a few years, 3, 4 years, 5 years under heavy use. And then they start to give signs of failure ahead of time so people can kind of do something about it. But I don't know if there's really a great there's not like a ton of data on this. And you just have to, it changes from generation to generation too. It's certainly, as people try to pack more and more bits into the same, into each individual floating gate, like it becomes, like it's more likely to wear out more quickly. Because what happens is it just becomes harder to differentiate the charge levels is why that becomes, the wear out is an issue. Yeah. Yeah, that absolutely, you could imagine that's the case, that you can kind of have a device that, like, once you see that there's an initial problem that you can't sense the data and you're getting, because what you're going to do to be able to sense the problem is you're going to put some error correction and stuff into the device, and you're going to say, this doesn't make any sense. I'm like, this block is no longer readable, and I can map it out and not use it anymore. But it's also indicative of, it's because you've been doing wear leveling, it's probably going to start happening a lot pretty soon. So it becomes an early warning sign of, you're probably going to stop using this SSD. But yeah, sure, you can kind of map it out at the beginning. Good question, yeah. So what's the exact case that you're talking about? Yeah, so I mean, you're actually always doing that, right? You're always, when you have a block, right, you're always, with log structuring, you're erasing the whole thing, and then you're programming each page beginning to end, right? But that's okay. There's like some thousands of pages per block. So you're only paying that erase cost once, the few milliseconds, for many, 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 many milliseconds of programming. So no matter what you're doing, the log structuring kind of minimizes that cost. And even if we're writing the same thing over and over again, well, first we'll write it here, then we'll do it to the next one, and then we'll kind of keep writing it to new locations. And sure, we'll pay an erase for each, every so many for every block, but that's just once per all the programs. Does that make sense? Good. Any other questions? Yeah.
Maybe a little off topic. Do you ever have wear leveling in Distrat? Or is, I guess maybe it's the secondary question. Is there a concentration of that information in Distrat?
Yeah, that's a good question. So the hard drive doesn't tend to wear out by like writing in a particular location. It wears out as a whole because of mechanical wear out. So like, at some point the arm motor won't work, or the rotor won't work, or some other issues will happen. But writing, like, you can write the same block over and over again, and the hard drive does not mind that at all. It's just encoding, magnetic charge, and that there's no like wear out notion in there. So that's quite in contrast to the Flash, where it's really on a block-by-block basis. That's a good question. So definitely different failure modes. So why don't we do a very late, quick stop, we'll reset, and then we'll just kind of end class. How sad is that? Very sad is the answer. Okay, thank you.
What are the storage say on the phone you SSD?
Usually SSDs.
So you said that so SSD were also like 5
Well, under heavy use.
Does that mean like if we buy like a laptop, we change it every 5 years?
No, because you don't use heavy. How often are you doing I/O to your storage device? Very rarely, actually. So in a Facebook in a data center, it's 24 hours a day. It's getting written to. So then it'll wear out in 3, 4, 5 years. Your laptop, other things will break first. Yeah.
Thank you.
Yeah, sure.
So like I know like you all got something in this kind of form in a linear way.
Yeah.
But a bit like so in the this is circular, right? So basically for example you actually like writing like that, like going inside. So how does it work?
There's each track is a circle. It's not a spiral.
Okay, yeah.
Each track is a circle.
Okay.
So each of those are individual tracks, and within a track there are sectors. Like so, and so you can read or write each of those individually.
Okay.
And you know how that happens. It's encoding some charge there, and it's showing high and low charge. But it's
Okay. So basically when we go this is that goes to sector like that. Basically.
well, I mean, so a sector is 512 bytes.
Yeah.
So when we're writing all this stuff out, it's running to many of those within the track and then the third track.
Okay. So basically when we write.
Yeah, let's say, yeah.
Okay. Different backward. So like I know that we use a lot of calculations like so two and our sequence so we write. Right?
Yes.
Yeah. But then like because you are storing data first
Yeah.
and then I know and I map. So wouldn't the read be like some type point and then we have to go here and then go back again and go back again? Wouldn't it be better to do I map here, I know here and data? You know what I mean?
Oh, yeah, you should. You could do that.
Okay.
Yeah, I mean, the thing is, a lot of those, like iNodes and IMAP pieces, they tend to be in memory too. So you're mostly not reading those. Mostly you just want to do that.
Okay.
But yeah, sure, you could think about how to organize it.
Okay. Thank you.
All right. So we didn't solve all the SSD problems. You can read the book chapter for details about how people make the mapping tables smaller. There's a fair bit of detail on that. We can, by the way, we have an exam next, a week from today? Does that sound right? So do people want to do a review session at some point? Like, yeah. Like, okay, kind of yes. So I don't know when, like Sunday? No? Sunday's what? It's good for you, okay. Well, okay, we'll decide, but something like Sunday, we'll do a review session. The final is comprehensive, but certainly there's enough material in the file and persistence part of the book to really fill most of the exam, call it 60, 70% of the exam. But yeah, you have to remember a little bit about how a page table works, but not, nothing super detailed. You have to remember virtualization. You have to remember a little bit about concurrency, but it'll mostly be about the last piece because we only have so much time during the exam, and I can only torture you so much. So that's that. You have a project due. Congratulations, you'll be done soon. Hopefully you're enjoying seeing that in practice. So any other questions about that sort of stuff before we end? Yeah? all the projects equal weight? That was the original design, but it does feel like 4 is a little bit more somehow to me. Is that fair to say? So it will probably be weighted a little more, but if it turns out to be bad for you that it's weighted more, maybe I'll do it both ways and give you the max. So one or the other. But 4 just feels a little bit heavier, so it seems like it should be a little more. Any other questions? As you can tell, I'm a little too laissez-faire about that, but my apologies. You get old and you just say, it'll work out. And it's true, it'll work out. You will get a grade in the end. Okay, so here's how we're gonna end class. Oh, let's change the lighting. Off. All right, all good things must end. Even 5:37. Okay, so I just thought I'd talk about a couple things. And this is just kind of some things I've thought about as a student and then a professor over many years. I was kind of a professional student, right? Like at some point you're trying to explain to your kids what grade you went to. Like after 12th grade, you went to undergrad, 13th, 14th, 15th, 16th. Then I went to grad school, which was 17th, 18th, 19th, 20th, 21st, 22nd and a half grade. It's a lot of grades. And then I've been here for 21 years as a professor. First thing I always think about when I think about like any sort of advice is this kind of most basic thing. This is actually written in one of these earliest systems papers. Experience doesn't equal wisdom. What that means is you have experience all the time, but to turn it into wisdom, you have to think, like learn from your experience. So don't just have experience, think. It's really saying that, unexamined life is not worth living. Examine your life and think about things. So what I'm going to just talk about very briefly to end class is kind of realizations I had, mostly as a student, and then some regrets. And I realized I shouldn't end on the regrets, but that's how I'm doing it. So my apologies. One of the first things, I remember an English professor that I was listening to once said, education is really a selfish process. And that really surprised me. I had never thought of myself as a student as being selfish. But if you think of it, like all you're doing is trying to educating yourself. It's just for you, it's just for you right now. It's just a selfish process. The way it doesn't become selfish is after you're done with your education, you go off and are supposed to do something good for the world. So that kind of was surprising to me, and especially in a public institution, if you think of it, that means there are taxpayers who will never set foot on campus that are helping to support this entity. I was really struck by that when I don't know how many of you watched the announcement of a new building that we were building. Did anybody watch that? All 0 of you, 1 of you? Okay. I mean, okay, it's not the most exciting TV, I guess, compared to whatever else is on YouTube or whatever. But the donors, John and Tasha Morgridge, they went to school here in the 50s and, then eventually became billionaires, which is like a pretty good path. In fact, there's something about like Wisconsin, I don't know what it is, but like some years ago they did a study, did we talk about this, of like where all the CEOs of Fortune 500 companies come from, and like there were 2 schools tied at number 1. It was Harvard and Wisconsin. Yeah, how cool is that? And so Morgridge, and John Morgridge was the CEO of Cisco, which builds networking gear for many years, and that's how he became a billionaire, because it turned out networking, there was a lot of it that needed to happened and built in the world. But what he talked about when he was in the process of giving $125 million to help build this building, which is crazy that like someone can write a check and give $125 million. Actually, I don't know how that happens. I don't know if it's all crypto or whatever, but what he talked about was he thanked the long dead taxpayers that helped make his college affordable so he could actually come here. Now, if you heard how much he paid, you'd be really angry because he paid like, $100 a year to go to school here. So it's a much better deal back then. But still today, we're subsidized. And it's important to kind of recognize that, I think. It's a selfish process, and the way you pay it back is what you do after. So that's you. Another realization I had as an undergrad, I just remember waking up one day and thinking this, is like, I was at a big public school, similar to this one, but what was the difference? Well, it was in a different state. But it's basically the same experience, really. Like big public schools, big public research-oriented, good universities, all have a similarity. And what I kind of recognized is, like, I could die and it would take them a while to figure it out. And why is that important to me? It's because I realized I had to kind of take care of myself more. Like I had to, and I think this is actually one of the most positive properties of being at a public institution is you learn to be responsible for yourself. Most of you learn to be responsible for yourselves. And what is that? Because it turns out in the real world, that's how it always is. There's no like environment that takes care of you. You kind of have to take care of yourself. The way my wife and I would talk about this is we would say this phrase, which I think I wrote on here. There is no they. Like, I don't know if you ever are complaining about something, you're like, I wish they would fix this. I wish they would go and, actually read the Piazza Post. I wish they would do this. I wish they. At some point you realize there is no they, it's you. And I think that's something that you learn actually here, or you could learn here. The train going by is appropriate because we can have no class without a train. A second next to last realization I had, it was kind of about grades, which I always tell you not to worry about, which I think is kind of true. Like, you should worry about learning. But I had this kind of funny thing happen to me as an undergrad. I don't think I've told this story here before. I was kind of friends with this one guy. I mean, kind of friends. I mean, you know how like you kind of know people, you're in classes together and you kind of get to know them, but you're not quite friends, but you do projects together and stuff like that. And I felt like I was always helping this guy out, like in class. Did I tell this story already? No, okay. So I've always felt like I was helping this guy out. And then, like, we were applying for something, and like, we had to like write our GPAs down. And like, we're both a little sheepish. I don't know about you all, but we didn't talk about our grades too much. And then like, but at some point he wrote his down. It was like a 3.98, and mine was not a 3.98. I forget, it was like 3.6 or something like that. And I was like, how is it this guy, who I'm helping in every class that we take together, has a better GPA than I do? And it was another realization I had. And the realization was, he like works harder than I do. Like, this is a very important realization. It wasn't because he was smarter than I was. It was that he clearly was putting more into it. And this kind of funny thing happened. I just kind of recognized that I wasn't putting enough into each class that I was kind of like, oh, I'll do fine. And I did fine. But other people were doing better. And then, of course, what I was worried about is at the end, when someone judged us just by looking at a piece of paper, they would say, well, that guy clearly must be better at stuff than I was. And it kind of bothered me. I guess I'm competitive or something like that. And so I actually started working harder in school. It's 100% that moment, as I wouldn't be standing here if I hadn't had that moment. And what was kind of funny about it is when I started working harder, like I actually learned a lot more. It was also unsurprising. It's like really obvious, right? And I don't know if this has ever happened. You take an exam, and then everybody goes outside, and you talk about it, and you all commiserate, and you're like, oh, that was tough, whatever. And I remember after I kind of figured this out, I was in like a discrete math class, and I actually studied for it really hard. And it was like, the exam was exactly what was in the book. We came out, and I was expecting everybody to say, oh, what an easy exam it was, and everybody was talking the same way. They were like, oh, that was so hard. I'm like, no, it wasn't. It was all in the book. And what was the difference? Is people hadn't read all the book. How crazy is that? And it was just like this funny thing, the most obvious thing. So grades kind of don't matter, but you have to kind of figure out ways to force yourself to learn, because when you learn deeply, you do learn more. So anyway, that was the story of my buddy. His initials are PL. He doesn't know that I tell this story all the time, because that would be kind of weird. Realization, number one, is figuring out what you're good at. And actually, I've had this interaction many times. I think I talked about kind of, at least in some subset here, about working in a robotics lab. But I had this realization also. I was thinking of doing computer architecture. Did I talk about this at all? A little bit, right? So all the career paths I've taken before, or almost took, robotics and computer architecture, the reason I ended up not going down those paths is because I would look at people who are good at those things and realize they're like better at some parts of it than I was ever going to be. They had some skills, like as a computer architect, being really good at double E level stuff. As a roboticist, being good at like sensing and actuating. So you have to find things that, not just that you like doing, but that you're good at, because that's how you excel compared to the rest of the world. So I think it's something just worth thinking about. So those are my realizations. I'll kind of end with some regrets and then actually one last thing. Somewhat of a regret was the kind of classes I didn't take. And what I used to always tell people is and I've probably said this in here too, is pick people, who's instructing the class, not the class itself. You're never gonna learn enough. There's too many classes, there's too many things to learn. Find people you like listening to. I hope you've liked at least listening to me a little bit this semester. If not, that's okay. Some of you have already expressed that to me, actually, so that's okay too. But generally, pick classes where you like hearing what's being said at the front, because otherwise it's gonna be less enjoyable. You're just not gonna wanna learn it as much. And so I think about that. And I didn't pick any classes like that. I always picked on, I wanna learn computer architecture. Okay, next I wanna learn operating systems. Next I wanna learn compilers. And I just took classes. And literally, my undergrad experience was I got all the worst professors in almost every class I took. And it was really terrible. And I only recognized later that it was my own fault, right? I just kind of had an order that I thought I should go through for whatever reason. And I regretted that. A second regret really is around communication. I avoided communication. I've talked about this probably a little bit. I've avoided communication. I could not speak in front of people at all. Even by the time I was an end of undergrad, it petrified me. I just had a real fear of public speaking. And it turns out there's always a solution to it. You just do it. You just do it a lot. You get used to it. It's so important in whatever you do to be able to talk comfortably in front of groups about what you're doing. Whether you're a researcher or an engineer or whatever, communication is central, because then that's how you let people know what you're doing and can help change whatever the project that you're working on, the direction of something. It's done through communication. I used to, in fact, view almost everything other than the technical stuff I was doing as not important. Like in high school, I wasted so much of high school because I viewed kind of the humanities side of high school as not important, right? I was like, oh, math and science, that's important. I'll spend time on that. But English and history, I kind of ignored all that stuff because I figured, whatever, anybody could do that. And it was just a waste. Why would I waste that? So all these other skills that you can learn are right in front of you, and I think communication's one of them. So my last regret is probably the most important one, is people. It's people related. It's really easy to not connect to the people around you. There's all these people you don't end up meeting. Why? Well, I don't know why. They were sitting next to you in class every day, but you never spoke to them really, or never, said hello or whatever. Or the people you don't stay in touch with. I guess it's gonna be hard for me to talk about a little bit, but there was a guy I went to graduate school with many years ago. First class I took in graduate school, computer architecture class. We did this great project together. Super interesting guy. He wrote for Wired magazine as a 20-year-old. Just he didn't have a TV. He just read books all the time. Very interesting person. And I just learned last 2 days ago that he got in a bike accident and he died. And then I thought, when was the last time I called Steve? Steve Steinberg was his name. And it was I looked in my mail and it was 7 years ago. I had sent him a note and we just kind of never got in touch again. And those are the things that stick with you. Now, when you're young, you don't think about these things as much. But later on, you look back, you think about all the people that you can connect with and stay in touch with, and stay in touch with them even if they don't stay in touch with you that well. There's probably some people like that already, or somehow you feel like you're always calling them. It's okay. It's not gonna cost you anything if you call them twice as often as they call you. Stay in touch with people, because that's in the long run what you'll think back to, is all these people that you could have known or did know and kind of didn't get connected to or stay connected with. That's a regret I have, and sadly, I just felt it this week. So I told you it's going to end on a down note. So anyway, in final words, people always ask me this. They say, what was really important to your success? And I tell them something that's very unsatisfying, which is this words of wisdom I got. I got this on a golf course. Did I tell this story already? I never can remember what stories I tell anybody. That's a sign of old age. I was 12 years old, and my parents were we were going to San Francisco, and my friend who was a golf fanatic, he'd forced me to start playing golf. And he's like, oh, there's this great public course there. You should go play golf at this course along the ocean. It's public. So I forced my parents to drop me off as like a 12-year-old at this golf course in San Francisco, which, by the way, my parents found very funny. They're like, what are you, a businessman playing golf in San Francisco? But they just dropped me in. I was a 12-year-old, and I played with like these 3 40-year-old guys, played a round of golf. And one of them was this like Scottish guy. And I hit a shot, and it hit like a tree, and hit like another tree, and then like almost went in the hole. It was like right next to the hole. And they said, good shot. Everyone said good shot. They were being nice. I was 12. And I said, oh, it was just lucky, right? I hit a tree. I hit 2 trees, actually. And then the Scottish guy looked at me, all the important, suddenly laser focus on me. I remember this moment very distinctly. And he said, and I would do the accent, but I'm not going to do the accent. He said, never forget, luck is a part of the game. And I've just always thought of that. You know, things happen, and sometimes you get lucky. And sometimes, you know, like you can't really control that. What you can control is the weighting of the odds. So whatever success or failure you have in life, remember that it's not just this deterministic thing. There is some luck involved. In any case, we're over time. Thank you for a fun semester. And thank you. Thank you. And I will see you at the review session. Okay, thank you.